K5, a playground merry-go-round. So here in this problem, courtesy Derek Bridges and Flickr, we're going to look at a problem where we speed up from rest to get the thing moving with some kind of angular velocity, and then let go and let it come to rest. So the given in this problem is it takes 2 seconds to go from rest, no spinning, to 30 rotations per minute. Then 1 minute to stop. In other words, to come to rest. So you get it going and then you let go. So we want to know here the average acceleration, angular. So we're looking at the alpha, angular acceleration when we're speeding up, average, and then we want to have the maximum angular velocity reached. 3, the angle for this phase of acceleration. And then we want to know the average for the slowdown. And then we want to know the angle for the slowdown. So for solution for part 1, we want to know what the angular acceleration is. So we go from angular velocity 0 to some angular velocity omega, which is, now this is rads per second, so each rotation is going to be 2 pi. So this is 30 times 2 pi, and that's rads per minute, so I need to put 60 seconds down there. So 30 and a 60, that's going to be, well actually 2 times 30 is 60, so 60s cancel, and I get pi rads per second, pi radians per second. Now I'm interested in finding out here wants to know the average acceleration. So the average acceleration, now we assume the acceleration is constant, but really it's going to be the average. All right, so that would be using this kinematic formula. Omega is omega naught plus alpha t. And since this is 0, we can find the alpha is simply omega divided by t. The omega is pi rad per second, and the t is 2 seconds. All right, so 1 over 2 seconds. So this is going to be pi over 2 radians per second squared. Now you can work that out if you like. In fact, it's not a bad idea to just go ahead and put the pi in, divide by 2, you get 1.57 rad per second squared. This would be what they asked for in the problem. There we have it. Notice that we already got this in passing. Sometimes when you do problems, it's easier to do the second question first. So you already have this. Omega is equal to pi rad per second. I'm just simply noting that there. So omega would be 3.14 radians per second. So this is the answer to the second question, which actually found first. And then this is the answer to the first question. Now, what's the angle during this phase? Well, for the angle, we use 2 alpha theta minus theta naught is equal to omega squared minus omega naught squared. Remember our formula, 2AD is V squared minus V naught squared from translational kinematics, where this was X minus X naught. So now we're using this form. And with this formula, we have, well, initial angle by definition, we're going to call that 0 because we want the angle that it swept through. We have this is equal to 0. So this simplifies to 2 alpha theta is equal to omega squared. So that means theta is going to be omega squared over 2 alpha. Just divide by the 2 alpha, divide 2 alpha there to get theta. So this is going to be the omega here is pi. So this is going to be pi squared over 2 times, and the alpha here is pi over 2. That's interesting. So the 2's cancel and a pi cancels, and you just get pi. That's cool, pi radians. That's awesome. So pi is 3.14 radians. That's a 180 degrees. So when they were spinning this up, when Dad was spinning this up, Dad had to go basically run with the merry-go-round like 180. That's the angle swept out. Nice. Okay, now we're coming to phase, slowdown phase. So for the slowdown phase, it wants to know what the alpha is. Well, for the slowdown phase, we have omega, there's omega naught plus alpha t. Now here, these values are going to be different because this is a new problem now. The final omega is 0, and this omega naught is the pi. It's where we left off last time. This becomes the new initial as we're slowing down. So that's pi, and we're trying to find out what this is, and we know that's the alpha, and we know that the time says 1 minute. So it's 60 seconds. So when you look at this, you're basically looking at here, 0 equals pi plus alpha times 60. So the alpha is minus pi over 60. And that would be rads per second squared. So if you take 3 over 3.14, pi over 60, it's close to like a 20th. And that becomes here minus close to a 20th, 0.05 rad per second squared. Assuming constant acceleration, but really it's an average. And it's a deceleration, it's negative because it's slowing down. Then the angle we swept at here, the angle here, 2 alpha, theta minus theta naught idea, omega squared minus omega naught squared. This is the same kind of formula we used already once. And for the slowdown, okay, we'll take this starting with 0 because you want to know the angle swept out. And here the final is 0, so we got that. And then we have 2 alpha theta is minus omega naught squared, but see the alpha is negative. So we get a positive angle, sweeping out as it's slowing down. So the theta is minus omega naught squared over 2 alpha. And what is the value for omega naught? Well, we're going to go find it. There it is, it's pi. So this is minus pi squared. And then we have 2, what's the alpha? We go find it. It's minus pi over 60. I like to use the pi's here. And this would be, the minus signs cancel, and we get pi squared over pi divided by 30, and that is 30 pi. That's awesome. So that's like pi is 180 degrees, so it's like 30 times pi, 3 times 180. So you're looking at 15 rotations, because you remember every 2 pi is spinning around once. So this is equal to 15 times 2 pi, and this is one spin, see? So it's spun around 15 times during that minute it took to stop. Very nice problem. So if you want, you can work this out. 30 times pi, you get 94.2 rads, but I kind of think it's more interesting to just note that it spun around 15 times. That means more to me than 94.2 rads. Like, what's that?